So why should we devote an entire chapter just about water? Only on water. Because water is the what of our cells? It's a solvent, right? It's a solvent. So everything that's happening is happening in water. So to understand what's going on, we really need to understand water. And all the information here is a review of Chem 2. So we're reviewing Chem 2 here. So we're still in that review mode. So what we're going to be doing in Chapter 2 is spend a lot of time talking just about water, the geometry. We're going to do a little review of intermolecular forces and hydrogen bonding and talk about properties. Then we're going into acids and bases. And we're going to do some calculations. Not difficult ones. But you are going to need a calculator. If you don't have one with you, I'm not sure we're going to get to this, but make sure that you either have your phone or a calculator with you. I know the iPhone, if you turn it sideways, will have the functions that you need for this. So it's a solvent, as I said. And being the solvent, it's going to transport our chemicals. So everything has to be water soluble when it's leaving the cell. Because it has a high heat capacity. What's that heat capacity? What does that mean? Yeah, it stores a lot of heat before, it can absorb a lot of energy before the temperature goes up. Think about the beach, all right? Hopefully we're all going to go to the beach this summer, right? I know I am. So when you're on the beach and it's a hot day, like the next few days, you're walking across the sand. What happens to your feet if you don't have flip-flops on? They're going to burn, right? Because the sand does not have a high heat capacity. The sun is hitting both the sand and the water the same, giving the sand and the water the same amount. But what if you see a little drench that kids have made, a little low amount of water in there, right? You're going to jump in it like I do and have my kids yell at you for jumping in it. But it's going to be cooler because the same energy is hitting that water, but the water intrinsically can absorb more energy before the temperature can go up. So what percentage of us is water? It's 70% water. So it helps us maintain a constant body temperature, which is really important for our proteins. If we have wild swings in our temperature, then our proteins will all denature. We would not have life. So again, everything has to be dissolving in water. What part of the cell makes hydrophobic molecules water soluble? What part of the cell makes hydrophobic waste products water soluble? You guys remember that? This is just a little test. Did you look at this stuff last night? Smooth ER. Smooth ER does that. All right, so water. You think H2O should be a linear molecule, right? But oxygen has 6 valence electrons, group 6. And so it's going to end up having 2 lone pairs and 2 bonds with the hydrogen. So these lone pairs are a big deal. This is what ends up being the nucleophile in our hydrolysis reactions. The geometry is bent because with the 4 areas of electrons, it's going to be tetrahedral in shape, but the molecule geometry is bent. Now, tetrahedral shape, it should be 109.5, right, for the bond angles, but these lone pairs are fluffy, and they take up more space, so it squeezes this bond angle a little bit more. So water is a special molecule with some really interesting properties. And part of it, there's a couple reasons why it's so special. One is because it's a polar molecule. So what does it mean to be a polar molecule? You have to have 2 things in order to be a polar molecule. You have to have polar bonds, right? Remember I said that measure of polarity, the dipole moment, is a vector, right? So those polar bonds can't cancel. So there's two things. You have to have polar bonds, and the oxygen-hydrogen polar bonds, the electronegativity values are not going to be the same, so they're going to be polar bonds. And then that dipole moment can't cancel. So because of the geometry, they don't cancel. So a polar molecule is one in which one end is partially positive and one end is partially negative. That's the definition of a polar molecule. One end is partially positive and one end is partially negative. But it results from having a geometry and polar bonds.
So those are the two things that need to be polar, was geometry and polar bonds?
Yeah.
Okay.
The polar bonds, and then those polar bonds don't cancel because of the geometry. And we're going to show that in a moment. So that first thing, the polar bonds. Let's review polar bonds for a moment. I want to review electronegativity a little bit more. So remember I said some elements are bullies for bonding pair electrons. And which atom is considered the most electronegative on the periodic table? Do you remember? Fluorine. So that's the top right-hand corner. And so the general trend, it points towards fluorine. So it's going to point all the way to fluorine. So as you go along, from left to right, it's going to get more electronegative, and as you go up, it's going to get more electronegative. We don't have fluorine in biochem. So the ones that we're going to consider as electronegative atoms are going to be oxygen and nitrogen. And sometimes, if we're in the mood, sulfur. So oxygen, nitrogen, and sometimes sulfur are going to be our electronegative atoms. So a polar bond is one in which you have an electronegativity difference between the two. Linus Pauling came up with a scale where fluorine has a value of 4. Linus Pauling is one of my favorite scientists. He got wacky when he got old, but he was the only scientist I know that won a Nobel Peace Prize and a Nobel Science Prize. He got a Nobel Science Prize for the structure of proteins and a Peace Prize for working to end above ground nuclear testing. That's really cool, isn't it? I think that's, but then when he got old, he said everybody should take like 1 million milligrams of vitamin C to stay healthy. And maybe when you guys were really little, you might have remember where everyone was like vitamin C in everything, and all the foods had extra vitamin C, and that's because Linus Pauling was like, vitamin C can cure everything, and he was like, cancer can cure cancer. And what happens is it's water soluble. So once you take in a certain amount, you're just going to excrete it out. So I don't know. People used to take these big vitamin C tablets, and
people were dying because they were doing vitamin E, and it's not, can kill your liver.
Vitamin E is lipid soluble, right? So you can, and I'll tell you later when we cover vitamins, there's lipid soluble, and then there's water soluble, and the lipid soluble ones will bioaccumulate. And when I was a freshman, there was a girl on my floor that would only eat carrots. She had an eating disorder, and guess what color she turned? Orange, because the vitamin A is lipid soluble, got stuck in the fat in her skin. She didn't have fat anywhere else, but it got stuck in the fat in her skin, and she turned orange. It can really hurt you. You have to be very careful with these lipid soluble vitamins. That's really. I will not set foot in GNC. That is not regulated. It is a crazy, crazy world in there. Okay, so Linus Pauling, even though he's so awesome. Anyway, so fluorine got a 4. Oxygen is pretty close up to there. So what you're going to do is you're going to take your two elements that are in your bond, right? And then you're going to look at the difference between their electronegativity values. And if it's above 0, or less than 2, it's going to, or 1.8, it's going to be a polar bond. What happens if it's above 1.8? What does it turn into? Ionic, that's right. Good job. I wish I had a gold star. I'd put one right on your forehead. Anyway, so glad you're happy I don't. So here, you're looking at the difference. So oxygen and hydrogen, what is the difference between the two? 1.4, right? So that's a pretty polar bond. If I say you get to be ionic at 1.8, and the definitions change a little bit. So if the difference is 0, 2 nitrogens, maybe a sulfur and a carbon together, the difference is very little, then it's a pure covalent. They're playing nice. They're sharing those bonding pair electrons nicely. But if it's very different, all right, 1.4, the hydrogens, they're left out cold. They don't have really any electrons around them. The oxygen's the big bully, right? It's 1.4 above it. Now, these electronegativity values are relative. They're not something that we can measure. What we can measure is the dipole moment. And this is incorrect. You need to change your notes to have the arrow go the other way. So here you have 2 polar bonds. And the arrow for each of them is going to go from the hydrogen to the oxygen, hydrogen to the oxygen. So it's going to be like this, with my fingers being the heads of the arrow, towards into the oxygen. And so the net, when you put these 2 vectors together, when you add them, they get to be one big one this way, right? So the head of the arrow faces towards the oxygen, the negative part, and the end of the arrow is going to be towards the hydrogen. So what we have is a 2 vectors, 2 dipole moments from the 2 covalent bonds that are polar. And when you add those 2 vectors, they don't cancel. They actually add together. And so you get a net one that's the opposite of this arrow, and it points towards the negative part. So this side of water is very negative, and this side of water is partially positive. Now, let's talk about hydrogen. Hydrogen has how many protons and electrons? 1 and 1. 1 proton, 1 electron. The electron is in this bonding pair, right? But if that's being hogged towards the oxygen, then what is this out here? It's pretty much a naked proton just dangling out there, right? It's bare, all right? So you can think of it as it's pretty positive. So that makes this water really special. When you have hydrogen covalently bound to an electronegative atom, you have a situation where you have a naked proton hanging out there. All right, it is exposed. And because you have a positive exposed, some special things are going to happen. All right, so I mentioned that these vectors don't cancel. But let's look at carbon dioxide. These arrows are correct. Carbon dioxide has 2 polar bonds, right? Carbon and oxygen have different electronegativity values. Carbon was 2 point, I can't see that number, 2 point something, and oxygen was 3.5. So again, it's really tiny. Anyway, you know that it's polar. And so the polar bonds, dipole moments, because the geometry is linear for this molecule, those dipole moments cancel. The vectors cancel. So it is not a polar molecule because the dipole moments cancel. So even though you have polar bonds, the molecule is not polar because of the geometry.
Wait, I thought CO2 is polar? Or
No, it's not polar.
Okay.
Because you do have polar bonds, but the geometry causes it to be not polar molecule. So you can have polar bonds and have a molecule be not polar because the vectors cancel, the dipole moments cancel. In this case, I'm showing you they're equal and opposite. Okay, so it's a polar molecule, but it also has an especially lot of hydrogen bonding. And it's mostly because of this hydrogen bonding that water is so special. This property leads to very high boiling points compared to similar molecules. We're going to do a comparison. So hydrogen bonding is an intermolecular force between one molecule and another. The difference between a covalent bond and an intermolecular bond is energy. Covalent bonds are really strong. Okay? Intermolecular forces, even hydrogen bonding, are very weak. The way I like to explain it is covalent bonds, you need the acid in your stomach to break up, right? But intermolecular forces, you can break with your teeth. I'd be really impressed if you could break a covalent bond with your teeth. All right, that's not. So when you chew ice, you're breaking the hydrogen bonds between two water molecules. You're not breaking an oxygen-hydrogen bond, covalent bond. All right, so that's the difference. Your stomach acid doesn't do that either. That's a fairly strong bond. But anyway, I want you to think of it. It's weak enough for you to use mechanical strength to do it, which you can't do that with covalent bonds. So what is hydrogen bonding? There's two things. One, you have a hydrogen covalently bound to an electronegative atom.
Hydrogen bound to what?
An electronegative atom. So in our case, oxygen or nitrogen. So here you can see this hydrogen is covalently bound to this oxygen. So that's one of the situations. Then this naked proton on this hydrogen is going to interact with another electronegative atom. So the hydrogen, that hydrogen, is going to interact with another electronegative atom. So two things. One, hydrogen is covalently bound to an electronegative atom. And then the second thing is that hydrogen is interacting with another electronegative atom. It is the strongest intermolecular force other than ionic. And because it's so strong, when we draw molecules and we want to show the hydrogen bonding, we put little dashes or dots in between because it's such a strong force that it plays such a big role. Let's talk about intermolecular forces just a little bit more in general. When you go, and I mentioned this before, but I want to repeat it. When you go from solid to liquid to gas, the thing that you're doing is you're breaking intermolecular forces. In solid, you have the most intermolecular forces. They're stationary. They're all only doing is vibrating. So that's what you're doing. When you go from one phase to the next, the energy that you're putting in is not going into raising the temperature, but it's going into breaking those intermolecular forces. So going from solid to liquid, because liquid you can pour, the molecules are floating past each other, you are breaking some of the intermolecular forces. When you have gas, you don't have any intermolecular forces. So going from one phase, melting, you're breaking intermolecular forces. Going from boiling, you're breaking intermolecular forces. So those things, those substances with a lot of intermolecular forces are going to have higher melting and boiling points. So substances with more intermolecular forces or stronger intermolecular forces are going to have higher melting and boiling points because you need to break those forces in order to go from one phase to the next. There's many different types of intermolecular forces. They're non-covalent interactions. But basically what they are, they're either a positive to a negative or partially positive to a partially negative. That's what they are in a nutshell. They're the interaction of plus to minus. So we can have ionic, ion dipole, hydrogen bonding, what we call van der Waals, which these are, hydrophobic interaction, which very few people understand, and dispersive forces, which is the induced dipole. So ionic interactions, I mentioned, are the strongest. Anything with an ion, because it is a permanently positive or negative charge, that is going to be the strongest. But then this hydrogen bonding is then the next one. And then van der Waals forces are next. And so let's talk about the examples. We're going to go through each of these in detail. Aren't you so excited to go through each of these in detail? You guys okay here? Are you all with me with this? All right, I know. I understand. This is really tedious. I understand this is probably the most tedious part. No, there's one more tedious part. But of the semester, but it really is important for you to understand this as we go forward. And I want to make sure that no student is left behind, that we're all together on this. So can you think of an example of ionic interactions that's going to hold something together? And sodium chloride, right? Salt. You can still break apart. If you took a salt crystal, you can still break that apart, right? You can crunch salt. And what you're doing when you're crunching salt is you're breaking a sodium ion away from a chloride ion. So you can still do that. That's why it's not a non-covalent force. Ion dipole might be sodium around water, dissolving sodium. So dipole here I'm thinking is a polar molecule. So an ion molecule or ion sodium being surrounded by the negative part of water. And we're going to see that again later. Hydrogen bonding, of course, it's water. Other things can hydrogen bond. Alcohols can hydrogen bond. Yeah, sugars are alcohols, right? Our amino acids can hydrogen bond. Anything with hydrogen covalently bound to a electronegative atom. Dipole would be, say, ethanol to an ethanol. That would have hydrogen bonding as well. But something maybe with ketones. Yeah, ketones would have that. We're going to get through an example of these. Hydrophobic interaction is something where oil is going to be separated from water. And why is that? Very few people out there, if you walked around the Capital District and asked scientists to explain hydrophobic interactions, they would say that, oh, the oil attracts each other, and that is not the case. All right, so let's really understand this. So we're going to go through that in detail. An induced dipole is often called dispersion forces, and that is the case where you have nonpolar substances interacting with nonpolar substances. We're going to go through each in a moment. But one more thing about the strength. Let's look at the kilojoules. This is in calories, this is in joules. Covalent bonds are, in order to break them, you need to put in greater than 210 kilojoules per mole. That's a lot of energy. But all of these other ones, you can see, are less than ionic, which is the strongest, 80 or less, right? Hydrogen bonds, 30 or less. And those dipole ones, 9 or less, and hydrophobic interactions are small. So you can see that they're much less than half. So you can see that the energy that's held within these interactions is much less. Okay, so ionic interactions. Now, we're not just going to be talking about these interactions as, in a Chem 1 sense. We're going to apply them to our biomolecules. So again, it's going to be in between charges, actual charges, an ion. And side chains of amino acids can be charged. And so what happens, here's an acidic side chain, which at neutral pH is going to be negatively charged. And here's a basic side chain that at neutral pH is going to be negatively charged. What I'm not showing is the backbone of the amino acids, so I'm just showing the side chain here. And so what happens is the negative anion is going to interact with the positive cation. And when you have an anion interacting with a cation, it's called a salt. Salt is not just sodium chloride. It's any cation interacting with any anion. And so that's what our salt bridges are. So that's an ionic interaction. Very important in our structures of proteins. Now, an ion dipole is, the example is the salt, sodium chloride dissolving in water. So when salt dissolves, you put salt in water. Maybe you're making some pasta. You don't want the pasta to stick, right? So we all put a couple shakes of salt in there. And what happens is the salt's going to dissolve. It's going to dissolve right away. It's very soluble. But when the chloride dissolves, what it is, it gets surrounded by the positive part of water. When the sodium gets dissolved, it's surrounded by the negative part of water. We call this spheres of hydration. So let's look back at those salt bridges. Where in the structure of proteins, on the inside or the outside, do you think you're going to find them? On the inside. Why? What would happen if those anions or cations were on the outside? They would be surrounded by water, right? And they wouldn't see each other. They'd be masked by the water. So salt bridges have to be on the inside of our proteins in order to stay away from water. Okay. Weaker than this interaction is our hydrogen bonding. And one thing that makes water so incredibly different than similar molecules, even other molecules that can hydrogen bond, is that we have 4 possible hydrogen bonds per molecule. That's a lot. It's a little baby molecule, very small. But we have 4 possible interactions with hydrogen bonding. So again, we already defined hydrogen bonding, but I just wanted to mention that water is our biggest player, and these interactions make the boiling point and melting point so much higher. Now, in solid water, also known as ice, you have all of these interactions in place. When you have liquid water, some of them are broken. So when you have water, not all of the possible hydrogen bonds are in place. When you have steam, it's very dispersed, then there's no hydrogen bonding. They're completely away. Some steam, you can see little droplets, but when the water's away from each other, then there's no hydrogen bonding. So as you go from solid to liquid to gas, you're losing some of those. But in solid water, you have 4. Now, remember density? Density of substances is greatest when it's solid, right? Then liquid, it's less, and gas, of course, it's much less. But what about ice on a pond? Where does the ice go? The top, but that's solid. Why doesn't it go to the bottom? Because of I'm introducing this now because it has to do with hydrogen bonding. So it's because of hydrogen bonding. All right? So 50 years from now, when I see you on the road, I'm going to say, why does ice float? Most students, when they see me in non-campus settings, just pretend they don't know me. So what we end up having is a lot of empty space because we get this 6-membered ring shape. What's in the middle? Look at this. This is water, the ice crystal. But what's in the middle of these rings? Nothing. So because the ice crystal has empty space in it, its density is lower. And what happens when we break some of these hydrogen bonds? The water molecule can then fit inside the space, so that density actually increases. So another thing is that when something melts or boils, I said we're going to be breaking those hydrogen bonds or other intermolecular forces. And because water has those 4 chances to hydrogen bond, as opposed to the other molecules, they're not as strong hydrogen bonds. Methane does not hydrogen bond. You can see, let's look at water to methane especially. Water has the hydrogen bonds. Methane is similar in molecular weight and geometry. However, there is minus 182.5, minus 161 for the melting and boiling points. So hydrogen bonding makes it much, much higher melting and boiling point. Even something else that does hydrogen bond, maybe not as strongly, because it's not as electronegative as oxygen. The nitrogen-hydrogen bonds do increase the melting and boiling point, but not as much as with the water. You guys have enough of hydrogen bonds? You got it now? All right. All right, so it can happen, well, let's see what it can happen. Not just between water and water, but water and alcohol, water and carbonyl, and an amine, and an alcohol, an amine and a carbonyl, and an amine and another amine. So you can see the different cases that you can have hydrogen bonding. So there's lots. These are important in our proteins and nucleic acids. We're going to see these types of hydrogen bonding later on, so this will be reinforced. So here we have van der Waals, and they're dipole-dipole. One is dipole-dipole. So let's talk about that. A dipole, or polar molecule against another polar molecule. Remember I said the carbonyl is very special. The carbon is partially positive, and the oxygen is partially negative. Well, that partially negative is going to be attracted to another partially positive, and so on and so on. And that's going to hold two carbonyls closer to each other. Induced dipole. Now, remember when you learned about where electrons were in a molecule? It's a probability, okay? And there's a natural swishiness or probability of where they might be. And so what happens is, here's methane. Right here, this is carbon, CH4. And it's a nonpolar molecule because the vectors cancel. In a tetrahedral, they cancel. So when a polar molecule comes by a nonpolar molecule, what we have is somewhere where it's induced to have a dipole. It's a temporary thing. It's very weak. But the negative part of the carbonyl is going to push the electrons to the other side of our molecule and cause it to temporarily have a positive side and a negative side. It's very weak. It's very temporary. Once this floats by, it's very easy to take apart. And then here's our induced dipole. This is also called dispersive forces. So here we have a situation where, just due to the natural swishiness of electrons, one side's negative and one side's positive, it's going to cause the next guy to be one side positive, one side negative. All right, that's induced dipole. So, or you can also say dispersive forces. That's what I taught in general chemistry. So this one is also known as dispersive forces. This one down here. So nonpolar molecules interact this way. That's how you can have in lighters butane, right? Butane can be a liquid. It's under a little bit of pressure, but it's a liquid because the butane molecules are interacting with each other and holding them together. And the only force, because butane is not polar, is the dispersive forces. That's why nonpolar things have a very low melting point and boiling point, because they only have this very weak force. But the longer the molecule, the bigger the molecule, the more dispersive forces there are. And so longer, bigger molecules have more dispersive forces, and then it will have a higher melting point and boiling point. So here's another look. Oh, these are permanent. When you have a dipole, that's a permanent part of the structure. So these are permanent dipoles, and that's a temporary. All right, so let's take another look at the van der Waals forces. This is our ion dipole and our dipole. So we can see this is where we're going to be dissolving ions, our ion dipole, and dipole or maybe dissolving alcohols or ketones in water. So the process of dissolving is important. Intermolecular forces are important in that process. Now the last non-covalent interaction responsible for nonpolar molecules coming together when placed in water is hydrophobic interactions. So why doesn't oil dissolve in water? It's not because the nonpolar parts attract each other so strongly. It's because when you have, so say this is a nonpolar substance right in here, look at the structure of water around it. It forms this cage. And when you have a cage, that means order. Do you guys remember the term entropy? Then entropy is a thermodynamic term talking about the order in the universe. And it is always spontaneous to go from order to disorder. So anytime, just like my life and your car doesn't suddenly become clean, right? Your house doesn't clean itself. It was always very spontaneous to go from order to disorder, and you have to put a lot of energy in order to go to back to order. So having this oil droplet in here means that we have to have this ordered structure of water around it. That it goes against the thermodynamic term entropy. So think about your salad dressing, oil and aqueous vinegar, right? When you shake it, you're putting in energy, and you create lots and lots of little droplets of oil. Because if you didn't do that, when you poured it, you'd get a salad of oil. It's kind of gross. So you shake it up, and then you have these little droplets. And around all the little droplets is this ordered cage of water. So the more droplets you have, the more surface area you have. The more surface area you have, the more cage you have. So what happens after a few seconds is those oil droplets try to make the least amount of surface area so that you have least amount of cage. And what is the least amount of surface area? The one level. So it gets pushed out. So it's excluding because of this ordered cage. Did anybody hear of this before in any of their classes? You've heard about this? Okay, that's excellent. Because most people haven't heard about this. So this is why oil and water don't mix, because of this entropy-driven process. So anything nonpolar doesn't want to be on the outside, because you'd have to have that ordered cage. So if you have nonpolar side chains on your protein, they're going to go, it's an entropy-driven process to fold, because you don't want the nonpolar ones on the outside, because you'd have to have the cage of water. So the driving process, or the driving force behind folding of proteins is entropy, because we do not want to have that cage of water around it. That comes to these terms hydrophilic and hydrophobic. We talked about it before. So anything that's hydrophilic will tend to dissolve in water. Hydrophobic will tend to not dissolve in water, water-fearing. They're not really afraid of it, but we know now why nonpolar things are hydrophobic, because we don't want that cage. And amphipathic means that they have kind of both. You have a region that likes water and a region that doesn't. What biomolecule is amphipathic that we looked at? Has a long part that's nonpolar and a small part that's polar. Yeah, our phospholipids, or even our fatty acids. It has that polar sodium, the carboxyl group, and then the nonpolar tail. Soap. It's made from fats. What they used to do is take animal fat and treat it with lye, and what you would get is the salt of a fatty acid. And so what you have is a very polar part and a long nonpolar tail. And this is how soap works. So if you have greasy hands, say I have a little piece of grease on my hand, that nonpolar tail is going to dissolve into that grease. And then on the surface of that grease, you're going to see the sodium, or the water-soluble part. And then water is going to come by, and it will dissolve that grease. In my cells, you're going to have the nonpolar parts away from the water and the polar parts facing the water. That's how our micelles. This is how our lipid bilayers are going to be away. And then there is some temporary induced attraction between the nonpolar parts, but it's mostly that hydrophobic interaction, keeping that nonpolar part away from the water. Okay, so here we have a nice little summary of anything that's hydrophilic, anything that's going to have similar intermolecular forces with water. Anything that's ionic or can hydrogen bond, anything that's polar is going to be soluble in water or hydrophobic, philic. Hydrophobic things are going to be the nonpolar things. Or Our fatty acids are also going to be hydrophobic because that nonpolar tail is going to be, it's going to take over the properties of the molecule.